So hello everyone. My name is Vikas Kumar Singh, and we are going to solve some problem again from the sheet metal forming class. So if you are attending the online lecture, NPTEL SWAM lecture, so you might have came across the mechanics of sheet metal forming, where we are now at the stage of punching drawing process. So we are going to solve some basic of sheet metal drawing, and I will explain one by one, and then yeah, then we will solve some problem, and then we'll see, like, we'll see one by one the step and methodology and whatever nomenclature is there. So we'll start with some basic of seat punching process. So if you have attended the lecture, you might have heard about the word what is punch, seat, die, all this thing. You have heard about all these things. So I'm just revising all this thing for you. Like, it will be better to understand all this basic concept one by one. So in the sheet metal process, like if we are talking about the drawing, deep drawing or cup, making a cup, it's like a process where we have a die. We have a die like this. Suppose we have die. Okay, and we are keeping one sheet over this die, metallic sheet. So metallic sheet will be something like this. Metallic sheet we are keeping like this. Okay, and we are forcing from the top like this from here to here we have gap hole. So we are forcing from the top using a punch, and this punch is like this. So this punch is like this. So when we will apply some load over here, this will go inside this. This will go inside this, and we have die, similar die, like similar same kind of die is there like this. So some terminologies are there, like we have here some fillet radius here to avoid the crack and all. Similarly, we have some fillet radius here, some radius is there to avoid the crack in the seat, all these things. So all these terminology are there in the class if you have attended. So one by one we will see. So here I just wanted to explain you, this part is called punch. Okay, this one. And this is our seat, metallic seat, and this is our called die. Okay, so when we'll draw this, this will become something like this, something, some cup kind of thing will become like this. So this part is generally called face of the cup, and this is called bottom part of the cup, and this one is like this is either we can say it is with the die, or here this corner section we can say. So high stress at this point is the higher as compared to other part. So in this process, how, if we will see the cross section, if we'll just take the side view, the cross section of this. So I'm just drawing one more figure here for your convenience. Okay, so so this is the side view of, this is the cut section of this cup. So you can see this is this portion. One, I have taken one portion of this. So this is the, this part. This is the bend part here over here. This part is the bend part over here. Okay, and this is the face where we are seeing this. This is the face. This part. Okay, this is the face here. Okay, so again here some corner will be there, and this part is the bottom part. So we have taken one section out from this. So this will look like this. Okay. Some terminologies are there that I would like to explain here, like a strain. Again, if we are talking about the principal strain in this case, so we have denoted principal stress as epsilon 1, epsilon 2, and epsilon 3. So here we have generally in one direction, if you are taking D1 is the in one major principal strain, and D2 in the direction of D2 is the minor, and the third one is the thickness direction. So if we will take a strain in all these things, all in all the direction. So the first one, if we are writing, so sigma 1 will be ln of d1 by d naught, and whatever we are writing, it's all a true strain. All are defined in the class. Just I am revising here for you, and this T2 will be ln of d2 by d naught, and epsilon 3 equal to ln of T by T naught. T is the change in thickness and initial thickness. Okay, all are this three strain. Okay, and now the next part is your strain ratio, and in the previous classes already it is explained stress ratio and strain ratio. So stress ratio was generally denoted by alpha, and this was sigma 1 by sigma 2, and similarly sigma 2 by sigma 1, generally it is written like this, sigma 2 by sigma 1, and strain ratio was beta, and this one was written as epsilon 2 by epsilon 1. Okay, if we are writing in case of this sheet metal drawing, and d1 d2 is the two direction, like this is circular. Okay, this is circular in the direction of circular. So in one direction is d1 and another direction is d2, and the whatever thickness is there, like some thickness is there. So in the thickness direction, this thickness direction, we have a strain is called T. Means in that direction we are taking epsilon 3, and epsilon 3 we are denoting, we are writing ln of T by T naught. So if we are writing beta here, so the beta is nothing but ln of d2 by d naught divided by ln d2 by d naught, ln of this, and divided by ln of d1 by d naught, this one. So this will become our beta in this case. And similarly, if we are writing epsilon 3, so epsilon 3 was nothing but ln of T by T naught. And from the previous classes, if you have attended the online lecture, in that we have defined the relation between the thickness and other two direction D1 and D2, whatever D1 and D2 direction is there, other two direction strain is given, and beta is given epsilon 2 by epsilon 1. So we have just defined this in term of beta 1 plus beta into epsilon 1. Okay, so if we are just, we can write this. So all this terminology is like this. And now if you are familiar with all these things, and um, we can just process, we can just use all this nomenclature to solve some problem, so it will be much more clear. And all this beta business, beta epsilon business, it's already discussed in the previous classes. So better I will suggest to go to the lecture, online lecture uh, given by the professor, and then come back, then it will be easy for you to understand the problem. Okay, so we'll go to one problem. Yeah, here. So in this question, it is given, compare the tensions and the thickness at the point of maximum tension in a sheet. Initially, thickness is 0.8 G 0.08 mm thickness, with a stress strain characteristic is stress strain characteristic is given here. Effective stress is given 530 into effective strain to the power 0.246, and this is the value of N MPa. When deformed in biaxial, it is given here biaxial. So all you should remember, like what was the condition for alpha and beta for biaxial and all. So all this I will use directly because already it is explained, and the plane strain condition. Okay, so let us start solving this problem. So here we have thickness equal to 0.8 mm. Okay, and we have effective strain stress relationship, that is 530 into strain to the power 0.4246. So here n equal to nothing but 0.246. This is the value of n. Okay. And as I told, in the case of biaxial, we have alpha and beta both the values. So alpha is equal to 1 and beta is equal to 1. It means we are sigma 1 equal to sigma 2 we are writing here, epsilon 1 equal to epsilon 2 we are writing. Okay, in biaxial. So in the biaxial case, we have the effective at the stage of, in the biaxial case, at here it is given maximum tension at the point of maximum tension. So at the point of maximum tension, if you have seen the derivation, that at the point of maximum tension, the strain is denoted by epsilon 1 star, and it was related with n by 1 plus beta, and this formula was there. Okay. So this maximum tension, at that point we can calculate the strain, and that strain is going to be n by 2, and this value is going to be 0.123. Okay. Why we are calculating? All will be connected one by one. Okay. So thus the effective strain is, what will be the effective strain then? So effective strain is this one, and this is nothing but this value 2 into at the point of maximum strain, maximum tension, 2 into epsilon 1, epsilon 1, and this is going to be 2 into 0.124. This is star, whatever this is a star, sorry, this is 2 into 0.123, and this value is going to be 0.246. Okay. Now the thickness at the maximum tension is what? The thickness at the maximum tension. The thickness at the maximum tension. Maximum tension point. So here it is given in the question, thickness is the maximum tension point, and this is denoted by T equal to T naught of exponential, as already we have defined, derived this formula, minus of 1 plus beta into epsilon 1 star. This is the strain at the maximum point star, this value, and this one is given 0.8 and exponential of, and this one is minus of what? Minus 1 plus 1, 2 into this value is 0.123, and this value is going to be 0.8 into exponential of minus 0.246. And what is this value? So this value, if we'll calculate, it's going to be 0.626 mm. This is going to be mm. This is 6. Okay, this is mm. So we got the T value, thickness. We got the thickness at the maximum tension, point. Okay. So what would be the effective stress now? Effective stress at the maximum tension point. What would be that? So that value, if we are finding from this formula, 530, and this value is going to be this one, and to the power n value is given to 0.246. This value is already given, already calculated. So this is going to be 530 into 0.246 to the power 0.246. Okay, and this value is going to be 375 MPa. Okay. So this is the maximum, this is the effective stress at the point of maximum tension. Now, what would be the principal stresses? So in the case of, already we have seen what is the alpha and what is the beta. So alpha in the case of biaxial is 1, it means sigma 1 equal to sigma 2, and so this is going to be equal to effective stress. And now from here, if we are calculating a traction, traction means tension. Here traction T is generally denoted by T1 if I am writing sigma 1 into T. And if we are writing T2, this is nothing but sigma 2 into T. And this is the thickness. So traction can be easily calculated. And this value will be how much? So 375 MPa it is. So I am writing in SI unit. Okay. And into thickness is 0.626. This is in mm, so we can write it in meter now. And now if we are finding, this value is going to be 236 kilonewton per meter. This is the traction. Okay, traction, or you can say the tension. The principal tension is T1 or T1 equal to T2. Both the values are same. So principal, I can write here the principal tension are T1 and T2, and these value are this much. Okay. Now for the plane strain, now we have calculated all this condition for biaxial tension. Okay, biaxial tension, all whatever we have calculated. Now the next step is plane strain. So plane strain case. So plane strain case, we have alpha equal to 0.5, okay, and beta equal to 0. Okay. So now for this, if we are going at the maximum extension, the strain at maximum tension, the strain at the maximum tension, and that we have calculated epsilon 1 star equal to 0.246, and this value is going to be again n, same value, it's going to be n in the case of in this situation. And then next we have to find out what is the effective strain, and this formula 2 by root 3 already we have long back we have calculated this, going to be 2 by root 3 times of principal strain, say, epsilon 1, and what will be the effective stress, and this is going to be root 3 by 2 times of epsilon 1, sorry, sigma 1. If we will put all this value epsilon 1 and sigma 1, we will get the effective strain, effective uh, effective value of the strain and stress. Now the thickness at the maximum tension we can calculate. In the case of all we are calculating is in the case of plane strain now. So the next is the thickness at maximum tension T equal to T naught of exponential minus 1 plus beta minus 1 plus beta into epsilon 1 star, and this is the strain in the strain at the point of maximum tension. Okay, and now if we are putting all this value 0.8 exponential of minus 2 into 0.123, and this is again same value we have already calculated, so 0.626 mm. Okay, this is going to be this value. And now if we are further moving, calculating a tension T1 and T2, as we have already discussed T1 and T2. So T1 in the case of plane, T1 in the case of plane strain case, sigma 1 by T. And now if we are taking if this is major tension and T2 is the minor tension, so from the ratio of this, one more formula is there, like alpha, we can write alpha equal to T2 by T1, like same as case of if T is the thickness in the both, here it is the T1, T is the thickness, small t is the thickness in case of tension, in the case of sheet metal process. So we can write from here T2 equal to alpha into T1 also, this formula. And once we will calculate this value, we can calculate the T2 also. And from here, if we are putting the thickness value, this value and this value, and this value will be calculated from where? From here, this formula. Okay. So if we are putting, sorry, already this value is calculated. So if we are putting all this value here, so we will get the value of 28281 kilonewton per mm per meter. And if we will put the value of uh, alpha is 0.5, so this will be half of this, so it's going to be equivalent to 140.5. So I am just writing 140 kilonewton per meter. So in this case, what is the conclusion? So the plane strain at the maximum tension, plane strain at the maximum tension is greater, but the thickness at the maximum tension is same. So whatever thickness we have taken is same in the both the case, but the plane strain, I'm just writing here, the plane strain, at maximum, tension is but the thickness at maximum tension is same. Okay. So I hope it's clear. If it's not clear, we will go to the nomenclature with derivation of all these things. So I hope in next class I will derive all this formula so that it will be clear. It will be easy for understanding. Okay. So we will stop it here.